All right, so talking about this next topic. So in the previous class, we went into detail of uh, power control. You can say we had one inverter connected to the AC grid, and we wanted to control the power. And when we say power, real power and reactive power. And then we did that control through the medium of current because we wanted to limit the current. And we also did that in a stationary frame, in alpha beta, in AC frame. And we said these two, alpha and beta, the advantage was that these are separate and like a DC, like a single phase. So two single phase channels. So basically whatever we learned in single phase AC, we brought here and applied in three phase. However, for the reason of history and background, this synchronous reference frame is more common, has been more common, which performs the control in rotating frame. So I'm going to discuss that in this class. So rotating frame we discussed in the chapter, beginning chapter. This is the way it is defined. And then once mathematically defined, and once you define that, you can derive the equations of the converter, and that the coupling terms obviously are there. These are the coupling terms. And also we use this vector notation or matrix notation that we have, very convenient. And by the way, this notation here is very nice because if you put this equals 0, this is valid for alpha beta. And if you put this Cm equal to this matrix here, now this represents the dq domain. So this representation is valid for both alpha beta and dq depending on whether Cm is 0 or this given matrix. Okay. So basically there is a coupling between the two channels. Control structure. Control structures now in the dq says, okay, I take the current and I convert it to dq. To convert it to dq, I need a theta, and that theta comes from PLL, right? PLL also helps with to generate the reference current from the set points of the power. And that reference current must be limited also here, and then go to the current controller, and then current controller generates dq, mdq, and then convert it to ABC using the same theta, and then goes to the modulation. So that's the general structure of the controller. Let's look at the first the current reference, this block here, current reference generation, and then we go into this one, controller. So current reference generation, if you look at the expression for the complex power that we had before, we expressed that in terms of alpha beta in the previous class. Now in terms of dq, it will be the same because one of them will have e to the j theta, one of them will have e to the negative j theta, and they cancel each other. So these equations are valid also. VDID plus VQIQ for the real power, VQID minus VDIQ for the reactive power. We have them. So I'm going to use these equations to derive expressions for powers. So if voltage, let's say for the positive sequence voltage, if this is the positive sequence voltage, right? What is this one? Now assume that the voltage comprises a positive and negative sequence. So voltage is a positive plus negative, okay. The current can be written as, again, positive and negative. Also assume that the transformation angle is equal to the angle of the positive sequence. Okay, this is the key. So, and that leaves room, flexibility to always change things if need be. But the common approach, common approach is this angle of transformation. What is this angle of transformation? So the common selection is this angle is the angle of the positive sequence of the voltage, of the grid voltage. So if the transformation angle theta is equal to the angle of the positive sequence, then the voltage and current vectors in dq becomes this one. So in dq, according to this definition that we just said here, this definition for dq, so you go with that one, and then tells you that the grid voltage will be Vp plus Vn. So it will have a DC term and a double frequency term. We call it Vd plus JVq. And then for current, same thing. This equation implies that Vd is this one and Vq is this one. So if it has no negative sequence, Vd is equal to the magnitude of the voltage and Vq is 0. If it has some unbalance, then there will be a double frequency ripple equal to the magnitude of that unbalance on both components, on D and on Q. On D is cosine, on Q is sine. Just a matter of little practice before we get to things. So in a balanced current situation, let's say again the inverter is supposed only to inject balanced current to the grid. So the negative part of the current is 0. So V into I star, this is the V, we just said V, and I, you go back to I expression for I and put all these equal to 0. This is 0, this is 0. This only remains this part. And then when you multiply, you will get a real part and an imaginary part. Real part represents real power. Imaginary part represents reactive power. Each one of them has a DC part plus a double frequency. So this is the DC part, and this is the double frequency. This is the DC for the reactive, double frequency for the reactive. So as expected, and as we said before, your real power and reactive power, if the grid voltage is unbalanced, but the inverter only injects balanced current, both of them will have pulsation. But the DC value should be equal to the set point. So the DC value should be equal to the set point. Really summarize everything and add the current limiting to that, we end up with this same diagram that we had before. Now remember, the difference between this one and previous one, in the previous one we multiplied this one into SDP, multiplied in SDQ, and then subtracted from. We don't have that anymore here. The reference for ID, the reference for IQ, because we are controlling in DQ frame, not in A, alpha beta frame. If the converter can feed or is allowed to feed negative sequence or unbalanced current as well, then the expression for real power becomes longer and for reactive power also longer. As we said before, this will be the set point, real power, reactive power, and this will be the pulsations. Again, we have 1 degree of freedom, if need be, to suppress the pulsations of the real power or reactive power, or also to make a trade-off between them. But we need to define what that trade-off exactly means. So if you, here the study I have done, just to keep it simple, is the case that we want to remove the pulsations of the real power. So for removing the pulsations of the real power, these are the conditions. So to achieve set point of the real power, to achieve set point of the reactive power, and to remove the pulsations of the real power. So if you supply this amount of negative sequence with this direction, then you can remove the pulsation of real power. So this is the structure that generates reference current for D and Q domain in unbalanced situation based on these equations. With the comment that still there is room for improvement here for if any one of you is interested to work. This is still open, and then in the simulations, I did not run this simulation for the unbalanced case in the previous class, if you realize, and only ran for the balanced case. If you go and run yourself the unbalanced case, because you will have the files, and you will try extreme unbalanced situations, you will see that the current limiting will not be satisfied very well. You start getting violated. And that's because this block works for a good part of the times, but sometimes it will not be able to manage. So there is room for working and improving this block diagram. But first you need to understand really how it works based on these equations, and then if you want to try to improve it. Okay, now here is the situation. If they are coupled, now we have two control channels, one D, one Q, and there is a coupling between the two. We can either treat them as separate or decouple them, because it's possible to decouple them, and then look at them as a separate channels, or just look at them as two channels together and try to also design a controller which is coupled. So the first approach will be single input, single output. The second approach will be two input, two output, or MIMO, multiple input, multiple output. So both of these I'm going to discuss in this class. This is the first one, CISO. What does it say? Again, these are the blocks of the plant or the inverter, right? And this is the controller. So there is a cancellation of this using this one. There is a feed forward here. And now this coupling that happens in the plant, we add a decoupling. So this cancels this one. And the same thing we do underneath for the Q. So if we successfully manage to do that without any problem, then we have removed the coupling, so we don't need to worry. We only design one controller for this loop, and we design one controller for this loop. And both these loops are like what? Like the single phase DC, right? That we started in the first part of the studies that we had. We already done that in details, right? So full bridge VSC that we discussed, or half bridge, or half bridge will be exactly the same as this one, half bridge VSC. So there is basically no challenge for designing this CC current controller. And I put CC1 and CC1 because both of them are the same. There is no reason for them to be different. And their design is very straightforward. We have already done it. But if you don't want to do that, so you don't want to remove these couplings, let them be there. This one you may want to cancel, that's all right, okay. This feed forward terms from VGD and VGQ, you can do that. You can even put a filter on top of them here. But because we are taking them, by the way, if you are taking this VGD and VGQ from PLL, which in this case we are doing, so you don't need to put filters on them because PLL itself operates as a filter. So now, because we do not remove the couplings, we say I will put a current controller, has two inputs and has two outputs. And inside the controller is not two separate channels. They are also together linked completely. And then it generates U1 here, U2 here. So this is MIMO approach. Okay. Okay, so first the CISO case. This is basically the same LQT for K1 and K2. I wrote down the equations this time rather than showing the diagram. Doesn't matter. And then you write down the equations, you apply the operator d over dt. This is exactly the same thing we did in chapter about DC converters, DC-DC converters. And then you come with a matrix 2 into 2, very simple. And then cost function will be Q into error, tracking error square plus Q2 into derivative of current square. And this is derivative of the modulation index. And then you run LQR, and then you increase Q until the poles are settled. So for CISO, it should be no problem in terms of doing it. For MIMO, what it says basically now, it says I took both of them, the integrating part and the non-integrating part, and I multiply into a matrix. So this is a matrix here, this is a matrix here, right? And I'm going to design this K1 and K2. So now I have like 8 coefficients, and they are all linked together. Okay. So if you really look at the equations and define the state variables properly, so let's define x1 and x2 as the state variables of the output of the integrators. Therefore, derivative of these state variables become the tracking errors, right? So you can put it here, and ID and IQ will be x3 and x4. So we have 4 state variables, but together now. They are not separate. Output of the 2 integrators in the controller and the ID and IQ. And now we have, this is the equation for the first state variable. This is the equation for the second state variable. This is the equation for the third state variable, which has coupling with the fourth equation. And this is the equation for the fourth state variable, which has coupling with the third one. Write it down as this standard form, A, B, E. This you can consider as some component that we will remove it after applying the transformation. And the controller is basically this whole vector into x. X is x1, x2, x3, x4. Has 4 components. So you see the controller combines everything. Does not ignore anything. For the first channel, uses the information of the second channel, and for the second one, uses information of the first channel. So we apply this transformation, convert the problem into a regulation problem or regulator problem. And now we have 4 state variables. The first and the second one are derivatives of the output of the integrators, which will be the tracking errors. So E1 and E2. And the third and the fourth one will be the derivatives of the currents, ID and IQ. And the inputs are derivatives of the modulation index in the DQ domain. And then we just choose Q1 and Q2, increase them. You may choose Q1 and Q2 equal, because these are really 2 channels that there is no preference between them. So we shouldn't give any preference to any of them. So you increase both of them together, and this one you initially put it 0, and then you fix this one if need be and increase the other ones. So I will show you in the simulation. So this was the procedure for designing the controller, both CISO and MIMO. CISO already we did. MIMO, basically, this for the first time I explained for you here how to do the MIMO. Okay, so for CISO, this is what we did many times in the DC chapter. For MIMO, you have 4 poles that they move together. So once you first increase Q, all 4 move, and then you increase the other Q. So I chose these two Q together equal and these two together equal. So only you can say I can only have two Q. So one Q here, one Q here. All right. And then the matrix that you find is this one. Okay. Now, one interesting thing is that if you look at this matrix, it does not use any decoupling. It does not try even to use because it puts 0 here. And this was very interesting for me to observe for the first time because we always, with the CISO approach, we go and try to decouple. The MIMO optimal control says don't decouple, let it be there, and even don't try to decouple. Completely, absolutely avoid from decoupling because I'm going to use that coupling to improve my performance. Okay, so we'll see. So this, let's discuss first, and then we will go into the simulation. So this is the case that is balanced current, balanced voltage, and the power jump, and reactive power jump, and the grid voltage fault. The same scenario we discussed. And then we will see almost the same performance that we saw in alpha beta DQ, no difference. All the basic scenarios. Current limiting is done, power reference, real power, reactive power are done, no problem. If the grid voltage is unbalanced and current is still balanced, then the real power and reactive power will follow, but they will have pulsations. This is the case that a single phase to ground fault happens. You will have large double frequency pulsations on the real power and reactive power. This is double phase to ground fault happens. Again, you have large pulsations. The real power drops significantly because the grid cannot really absorb this power. But reactive power stays around 0, no difference, but real power significantly drops. Both of them will have a lot of pulsation. Now, here, this simulation says the grid voltage is unbalanced and the current also will make it balanced in order to remove real power pulse. But it does not remove. Right. I forgot the reason why, but I will find out. If you know, tell me.
The negative sequence component you are not regulating. If you see only D components are regulating, but to make it zero, the pulsation zero, you need reactive that negative sequence component necessary to be present in the current. So I think those negative sequence components are not being regulated perfectly. That's why this pulsation is there.
Okay. Let me see what I've explained here.
Are we taking care of negative sequence component of the current?
Yeah, I followed these equations. Followed the equations to remove the pulsation, and we calculated them this way. So theoretically, we followed all the steps. But why it didn't work, let me find out. There was a little thing that caused this one, which we need to fix.
Actually, I have seen one paper where they have separate loops for positive sequence and for negative and they are able to do that.
Yeah. No, I'll solve it here, but I just wanted to see, I don't remember now exactly what happened that this ripple stays there. Let me find out. What figure is it? This is figure 741. I should have explained in the text. Okay. Once. Okay. 741 shows the inverter responses when the grid is unbalanced and the inverter generates an unbalanced current to remove the real power pulsations, according to figure 7.32, which is that block diagram. The controller succeeds to yield a soft start, execute real and reactive power commands, generate sinusoidal current, limit the converter current, however, fails to remove the pulsations. The reason is that the PI compensators cannot accurately track or reject double frequency. Yeah. Because we are using what? We are using PI, right? I, integrator. Integrator is guaranteed to remove the DC errors or to track the DC commands. Now, we would like to follow or track double frequencies, right? In this case, we want to reject these pulsations. If you want to reject these pulsations, a PI cannot, it improves, but it cannot completely remove it. PI compensators cannot accurately track double frequency disturbance. Then we need to use a PIR. So we need to use, and this is the weakness of this approach. Despite this, people always have been using, and kind of because of simplicity, using it. But here it will clearly shows that if the grid voltage is unbalanced, and then you want to inject unbalanced current to the grid to remove the power pulsations. Using a stationary frame, we had no problem. We discussed that, and there was no. Here, immediately we realized, oh, it doesn't work, a PI. So now we need to add an R. But really, one of the main reasons that people always used synchronous rotating frame compared to the stationary, because they didn't want to use R. But now, if you really want to, it's complicated. So now you need to have a PI plus R. We'll discuss that in the next little section. But before going there, let's look at MIMO also. I mentioned here that in most of the ordinary or normal situations, even within the normal range of disturbances and uncertainties, we checked CISO and MIMO work very similarly. However, if you really push the system to the extremes strongly, you will see now the advantage of the MIMO controller. The MIMO controller the CISO controller starts losing stability and showing oscillations, but the MIMO works well. For instance, one of the situations I did, let's say a grid impedance of 2 millihenry is added, and the filter inductance is increased. And now figure 43 and 44, this is for the CISO, and this is for MIMO. I wish I had them in one page, but if you really can, I will go a couple of times on this one and the other one, try to keep it in your mind. If you look at the transients of these waveforms, this is for MIMO, not necessarily during the current limiting, even that's fine, but look at these transients that you get on the current of the converter. And this is the extreme case that you have an impedance at the grid side and increased in the impedance of the filter. And this is the CISO. You see, the system starts oscillating. More oscillations. And if you keep increasing it, let's say from this 2 millihenry, you go to 2.1, 2.2, 2.3, because you have to go very fine. Especially with the grid impedance, typically grid impedance has significant impact on the stability of the converters, the weak grid situation. I did not cover weak grid conditions in my lectures because that would take maybe at least 2 or 3 classes itself. So if you want to test it in the simulation, just go from 2, 2.5, 2.1, 2.2, 2.3, and just look at the simulation. And you should observe the oscillations that are happening here in the CISO and in the MIMO. So this has a stronger responses, so it becomes retains stability for larger values or impedances compared to that one. So this was one scenario. You can think of what other disturbances or uncertainties may happen in the system. I only looked at the grid impedance. And this is now PIR. I don't want to spend time with it because I'm not really convinced that this is the way to. I don't want to advocate this approach. Because if you want to use R, why not doing it in stationary frame? In a stationary frame, you only use R, resonant, at the fundamental frequency, and then you get everything. Here, you need to use an integrating and an R in the double frequency, which is even more demanding than single first frequency, and then but you will remove the problem. For the sake of education, it's good. So this is CISO for that one, and this is MIMO. And the problem becomes really huge. So these are PIR designs. You have PI and R, resonant at double frequency. So even for CISO now you have 4 poles, and for MIMO you have 8 poles. And now you see the pulsations of real power are removed. And this is extreme condition that you see oscillations are happening. When you push it to the extremes, you will see the system starts getting loose and showing oscillations. This is MIMO. Yeah, that was for CISO, and this is for MIMO. So you see the oscillations are a little bit lower if you compare this one with this one. Just keep this in mind in a moment. And now look at this one. So MIMO is better. But how much you need to define and quantify in a more scientific way, which I haven't done. That was not my intention to do. So if I want to conclude the VCC, vector current control, we did it in alpha beta and we did it in DQ. And we showed that if the grid voltage is unbalanced and the controller is desired to feed unbalanced current, the PIR compensators must be used. However, in the stationary domain, only using the PR solves the problem. And then you can add the DC offset rejection is done in a stationary domain by adding an integrating compensator if need be. However, if you want to reject the DC in in synchronous frame, you need to add another resonant at the fundamental. And the current reference generation and limiting almost similarly in both approaches. So the conclusion is that it seems like a stationary frame is simpler and more advantageous, even though the rotating frame seems to be, at least in industry, it seems to be more common. in academia, people are paying more attention to stationary nowadays. Let's see if I have this simulation. The power circuit as before, and this is the CISO controller in DQ, not in alpha beta, right? So the reference currents are DQ. And here we don't have resonant, we only have integrating. So one for D, one for Q, right? Then bring it here, feed forward terms, current reference generation and limiting is done here in DQ. And PLL is the same as before, same thing. I think this is the CISO. For MIMO, the only difference here is in your controller, right? So I summarized everything in this block, small block here. K into, so K into X equals U. So K is defined in the parameters in the simulation. So the input to this K, X, is a state variable of the first integrator, a state variable of the second integrator, ID and IQ. So all of them, they come, multiply into K in a matrix form. So K is a 2 to 4, 2 into 4 matrix. And that gives you U. Then here are the feed-forward terms. The other parts are exactly the same. And the design of the MIMO, let me see if I have the, okay. So the CISO design is as we had before. We actually ran this several times before. For MIMO, you only need to redefine your matrix A and B properly. So now your matrix B is also a matrix, it's not a vector. But other than that, the procedure is exactly the same thing. So you have now 4 Qs, Q1, Q2, Q3, and Q4, and then run LQR, and so on. Well, let me run this part. So this is the CISO design. And this is the MIMO design for only integrator, not resonant controllers. And simulation we can also run. Let's at least run one of them. So this is the result of simulation, initial synchronization, then starting of the converter. Set points are 0. And then here, real power set point to 10 kilowatt. So a current of about 40 amperes. Reactive power set point back to 0. It is shown here. Real power, reactive power. And then current limiting. And then back to normal mode. Any questions? No? All right, I think I will conclude the class at this point. Any comments, Chandra? Anything? Yes. Yes. Reactive power. This one here. So what would you expect? Yeah, that's right through. Did I discuss right through? No, I did not discuss right through. Okay. That's completely different topic. Whether you want to have a right through, what is the right through that you want to do? There are tons of different right throughs out there. So this one? Okay. See, when you have harmonics, for instance, in the grid voltage, and you want to prevent them from going to the grid current, right? So if they are in the grid voltage, and we discussed that they will, through that transfer function that we showed, they will go to the current anyway, so you have to stop them. And then we put resonant converters, resonant controllers at that particular harmonic 5, for instance, or harmonic 7. So if you really want to remove one harmonic completely, you need to put a resonant controller for it. But this is not really practical if you have many harmonics and you want to remove all of them. Even though we know in practice, in power system, even though we have all the harmonics in a practical power system, but only 5 and 7 and 11, these are really the dominant harmonics. Harmonic 37 is there, but it's very tiny. We don't need to do anything about it. So in the worst case scenario, I would say if you have a few of these resonant controllers, you will be able to handle the harmonics. But is there a way of combining these resonant controllers and then just with one controller do the job? That's also one good question too that you can think about that. All right, so we can stop here. Thank you, everyone.